Welcome to Weather Variables, Unit 1 of ATM101 Weather and Climate of Alaska. My name is Richard Collins and I will be your instructor this semester. This unit is about how we use weather variables to describe the atmosphere and supplements Chapter 1 of our textbook, Weather, A Concise Introduction by Gregory Hakim and Jerome Patou. The primary meteorological variables we use to describe the weather and climate are temperature, pressure, wind, and precipitation. By collecting these variables on a daily basis over years, we understand how the weather varies from one day to the next, or how the climate changes from year to year. Observations are essential to understanding the natural world. In this class, you will learn how to make observations and analyze the data that you collect. In this first unit, we introduce the weather variables that we will use for our in-depth study of weather and climate this semester. Before we begin, let's remind ourselves what the atmosphere is. The atmosphere is the thin layer of gases, liquids, and solids that surrounds the Earth and maintains life on Earth. The word atmosphere comes from Classical Greek, atmos meaning humid or moist, and sphere meaning ball. It is telling that it is the humidity that is recognized as a defining characteristic of the atmosphere. Humidity is part of the hydrological cycle that is so critical for life on Earth. The science of meteorology is the science of things that fall as meteors fall through the atmosphere from the sky. How we observe and measure the atmosphere determines how we understand it. There are 7 variables used to describe our weather conditions: temperature, pressure, wind and precipitation, which we discuss in this unit, and also clouds, humidity, and visibility. From the International Space Station, we see how the atmosphere gets thinner with height and eventually thins out so that the moon appears in a black sky. Looking down on Earth, we see that the atmosphere is cloudy, with clouds forming in swirling patterns, thick clouds in the tropics, and a hurricane off the coast of Brazil. This semester, we will explore the meteorological processes that explain these patterns. Temperature is the most commonly used meteorological variable and one of the most important variables used to describe the atmosphere. Temperature is a measure of the amount of energy in the atmosphere. The atmosphere is made up of a mixture of gas particles, called molecules and atoms. These particles are in motion and have kinetic energy associated with that motion. It is this energy that we call heat. The slide shows a cartoon of gas particles in motion. The particles move faster when they have more kinetic energy and move slower when they have less kinetic energy. A gas at higher temperature has higher kinetic energy. When a hotter gas and a colder gas are mixed, the faster particles of the hotter gas collide with the slower particles of the colder gas and lose energy to them, so that the faster particles slow down and the slower particles speed up. The mixture of gases now reaches a new intermediate temperature that is higher than that of the colder gas and lower than that of the hotter gas. Thus, energy is transferred from the hotter, more energetic gas to the colder, less energetic gas. Thermometers measure the temperature by changing an observable characteristic in response to energy received from the gas. In a liquid thermometer, gas particles collide with the thermometer and transfer energy to the liquid of the thermometer. This transfer by vibrating and colliding particles is called conduction. The liquid expands as it is heated, and the length of the column of liquid increases as the liquid expands and the temperature is read from the length of the column. An infrared thermometer works on a different principle, where warmer objects emit more radiation than colder objects, and this is the radiation directly detected by the thermometer. In a weather station, the thermometer is placed in a louvered white box. The thermometer is shaded and well ventilated so that the thermometer is only heated by the conduction from the air that circulates through the box and is not directly heated by sunlight, nor does the sunlight heat the box like an oven. Furthermore, the box is at least 4 feet, about 1¼ meters above the ground, so that the box does not receive any heat from the ground. Temperature is reported in both degrees Fahrenheit and degrees Celsius. These temperature scales are based on specific physical processes. For the scales in the slide, we see that 32 degrees Fahrenheit is equivalent to 0 degrees Celsius and corresponds to the temperature where water freezes. It so happens that minus 40 degrees Celsius is equivalent to minus 40 degrees Fahrenheit. 212 degrees Fahrenheit is equivalent to 100 degrees Celsius, the temperature at which water boils. These commonly used temperature scales are called relative scales, as they are defined relative to specific physical processes. The Kelvin scale is defined as proportional to the actual energy of the gas particles. 0 Kelvin represents absolute zero, as it is the temperature where the gas particles have stopped moving and they have no kinetic energy. There is no negative Kelvin temperatures, as there is no negative kinetic energy. Because the temperature in Kelvin is directly related to energy, it best describes the physical state of the gas, and we use the Kelvin scale to relate the different properties of the gas, such as density and pressure. 0 degrees Celsius corresponds to 273 Kelvin, while 0 Kelvin corresponds to minus 273 degrees Celsius, the lowest possible temperature. Popular fiction sometimes report temperatures in negative Kelvin as a dramatic device. This semester, we will see that surface weather depends on meteorological processes higher up in the atmosphere, that is, the weather aloft. Thus, to understand and forecast the weather, we must have measurements of the vertical profile of the temperature. These measurements are made by radiosondes, where a payload on a balloon radios the meteorological data back to the ground. The word sonde comes from the French word for probe. While pressure, temperature, and humidity are measured by the payload, the altitude and wind are measured by the radar on the ground that tracks the flight of the balloon. Eventually, the balloon rises to an altitude where it pops and falls to the ground. Radiosondes launched at Fairbanks International Airport often fly to the northeast and come to rest in the White Mountains. We see on the plot of the temperature profile that the right axis is given in pressure units and that the pressure falls steadily from over 900 hectopascals at the surface to 200 hectopascals at an altitude of 12 kilometers or about 7.5 miles. We will see this semester how pressure is often used as a proxy for altitude. The atmospheric pressure is the pressure due to the weight of the atmosphere. If you feel under pressure, you are indeed, as there is a force equivalent to a weight of over 10 tons or 22,000 pounds pushing on you every day. You experience changes of pressure when you climb a mountain and your ears pop. You also experience pressure changes when you dive into a swimming pool and the pressure on your ears increases with depth. Pressure is the force per unit area and is demonstrated by the use of snowshoes. Snowshoes spread out the force of your weight over a wider area than your footprint and so keep you from sinking into the snow. As expected, pressure decreases with altitude. Because air is compressible, the air is thicker at lower altitudes than higher altitudes, and thus the atmospheric pressure drops more rapidly with altitude at lower altitudes than at higher altitudes. The atmospheric pressure was first measured using columns of fluid in an open pan. In a closed column, a fluid can rise freely as there is no back pressure from the vacuum in the top of the column. Thus, the fluid rises due to the force on the open fluid in the pan. A column of water will rise to a height of 10 meters, about 400 inches. Obviously, this is too long a column to be useful, and so scientists adopted mercury, scientific symbol Hg, as the fluid for barometers. Mercury has a density of 13.5 grams per centimeter cubed, that is 13.5 times larger than water, and so the column rises a much more useful 76 centimeters rather than 10 meters. The aneroid barometer uses a sealed container that changes volume as the exterior atmospheric pressure changes. The container is connected to a dial that is calibrated to give the pressure reading. Finally, electronics modernizes the aneroid barometer. A precise silicone membrane flexes as the pressure changes, changing the height of a vacuum gap between two electrodes. This change of the gap height changes the capacitance between the electrodes, and this change is detected electrically. These electrical changes are calibrated to give the corresponding pressure reading. We will discuss weather systems such as storms a lot this semester. Storm systems are eddies or vortices where the wind blows in a closed path around a low-pressure center. As the pressure at the center decreases, the winds generally strengthen. In fall 2025, Tropical Typhoon Halong traveled from the western Pacific south of Japan becoming an extratropical cyclone that crossed over western Alaska on its way to the Arctic Ocean. In the Bering Sea, storm warnings were issued to communities in western Alaska. Flooding and high winds in Kipnuk and Quiglingok resulted in widespread destruction of buildings and evacuation of the residents. The slide shows the flooding in Kipnuk and the actual and predicted path of the storm, where the X's mark the center of the storm. On October 12th, the storm tracked east of its forecast position. Dr. Rick Thoman at UAF has a very interesting article on the meteorology and social impacts of ex-Typhoon Halong in Alaska. Wind is air in motion. Wind is often the meteorological variable with the highest impact, both in terms of direct effects on humans and infrastructure, as well as the effects of the water it can drive in storm surges. Wind is more difficult to measure than pressure and temperature. Meteorologists often focus on temperature and pressure and derive winds from these two variables. However, pressure and temperature combined with direct wind measurements yields a more accurate description of the atmosphere. Wind is a vector, as it is described by both its magnitude or speed and its direction. The direction is measured clockwise from north. Wind carries the weather with it, so wind blowing from the north in Alaska generally brings colder weather. This is why we describe winds in terms of where they blow from, not where they are blowing to. Northerly winds blow from the north to the south. This is opposite to the professional physical and mathematical conventions used by scientists, where winds are defined in terms of where they are blowing to. A westerly wind is also an eastward wind. A wind blowing to the northeast is a southwesterly wind at an angle of 225 degrees from the north. Traditional anemometers use propellers or cups to measure the wind speed and vanes to measure the wind direction. The vane aligns itself with the wind and faces into the wind. More modern anemometers use ultrasound waves to measure the wind. Radars are used to measure wind profiles in the atmosphere as well. The word anemometer comes from the classical Greek. Anemos means wind and metron means measure. A note about knots. A knot is a speed of 1 nautical mile per hour. There are 60 nautical miles in a degree of latitude, so a speed of 60 knots represents a speed that travels 1 degree of latitude in an hour. A nautical mile is 1.15 miles or 1.85 kilometers. To measure a ship's speed, a sailor would use a line tied to a pie-shaped piece of wood off the stern or back of the ship. Knots were tied at uniform intervals along the line. Sailors would count the number of knots that had gone over the stern in a given period of time and hence calculate the ship's speed. We don't always have to resort to technology to measure stuff. We can estimate the wind speed pretty accurately from the effect of the wind on features over the sea and land. The Beaufort scale was developed by Francis Beaufort, of Beaufort Sea fame, an Irish hydrographer in the British Navy. The scale provides a consistent method for sailors to report the wind, an important skill in the days of sailing ships. As most of us are not sailors, the scale comes in sea and land version. Calm, with a Beaufort number of 0, indicates winds less than 2 kilometers per hour, or less than 1 mile per hour, or less than 1 knot. At Beaufort number 0, smoke and steam plumes rise vertically without any horizontal motion. Light air, with a Beaufort number of 1, indicates wind speeds of 2 to 5 kilometers per hour, where wind vanes remain still but plumes drift with the wind. However, last week at -40 degrees Fahrenheit, -40 degrees Celsius, there was nothing light about the light air that was present. This Beaufort scale slide is a bit of an eye chart, and a copy is available as a PDF. Wind is known for its variability. When we report wind speed, we do not want to report an instantaneous gust, but rather the sustained wind. The sustained wind is the average over time. Wind is also affected by the surface, as friction with the surface slows the wind. Winds over forests and cities can be slowed by friction due to the trees and buildings. As a result, winds generally increase with height. This increase in height contributes to the gustiness of the wind, as eddies sweep higher winds downward to the surface. This semester we will see how those higher winds aloft more generally control the weather systems at the surface. Precipitation, our friendly meteors, is one of the hardest quantities to measure, yet one of the most important as humans attempt to manage water resources in an increasingly populated planet. By using a funnel, the funnel rain gauge can collect a small depth of rain over a wide area and convert it into a large depth over a narrow area. This allows for a more accurate and precise measurement of rain depth. Measurement of snowfall is trickier. As snow falls, it settles and compacts, so to measure snowfall accurately, a scientist must clear the ground regularly and measure the small increments of snowfall on a snowboard that is placed on the ground. This is not just a science issue, but also impacts travel safety, as certain levels of snow accumulation are used to determine what level of operations are allowed at airports and what relief can be sent to communities. During a major snowstorm in 2016, the airports closed and I was trapped in Washington, D.C. for several days. At Reagan National Airport, the weather observers lost their snowboard during the blizzard, and so 20 inches or 51 centimeters of snow compressed to 18 inches or 46 centimeters. This event attracted national attention and highlights the challenges faced by weather professionals. They often have to make the most critical measurements in the most challenging conditions, for example storms, tornadoes, hurricanes, blizzards, cold snaps, heat waves, and floods. Snow gauges are tricky to operate as snow can stick to the gauge and the airflow around the gauge can change how snowflakes fall into the gauge. Snow gauges are surrounded by windshields to baffle the wind and allow the snow to fall into the gauge more steadily. Weather stations are increasingly automated to the extent that they can launch radiosondes automatically. The traditional weather station on the right is a well-ventilated white shelter that has the instruments measuring temperature, pressure, and humidity inside. The shelter is painted white to minimize absorption of sunlight that would result in the heating of the box like an oven. Furthermore, the station should be placed on a grassy rather than concrete or asphalt surface to avoid heat radiated from these heat-absorbing surfaces, again heating the box and contaminating the measurements. Automated Surface Weather Observing Systems, ASOS, measure cloud height and cloud cover, visibility, type and intensity of precipitation, rain, snow, or freezing rain, temperature and dew point temperature, wind speed and direction, and precipitation. Not only do ASOS document the weather, but they also issue weather warnings based on weather conditions, so they are not just passive observers, but also sentinels. The stations run by the Weather Service are called ASOS, and those run by the Federal Aviation Administration are called AWOS, as weather observing rather than surface observing stations. As automated systems, their data can be transmitted to the National Weather Service for real-time inclusion in weather forecasts. The map shows the locations of weather stations across North America and the neighboring seas. Clearly, there are a lot more weather stations on land than sea. At sea, weather stations float on buoys that are more challenging and expensive to deploy and maintain than the land stations. This is a challenge as the state of the oceans is critical in understanding weather and climate. To meet the challenges of observing the ocean, floats have been developed that measure their depth and the local temperature, pressure, and salinity. Thousands of floats have been deployed around the world. The floats drift for days at a constant depth, as well as moving up and down through the water column. In Alaska, there is a network of land-based surface observing stations operated by the FAA and NWS that is supplemented as the Mesonet of Oklahoma Climatological Surveys and buoys by the National Weather Service. There are 13 radio sites also across Alaska operated by the National Weather Service as part of the Upper Air Network and by the Global Climate Observing Program as part of the United Nations Framework Convention on Climate Change. Null School is a commercial company that creates maps of global weather and provides associated data services. Null School creates meteorological maps of the whole world based on forecast data from NASA supercomputers. The maps are updated every 3 hours. The slide shows 2 wind maps for 0300, 13th of January 2026 UTC, which is 6 p.m. 12th of January 2026 Alaska Standard Time. As expected, the winds are weaker at the surface, indicated by green colors, than the winds aloft at 500 hectopascals, indicated by pink-white colors. The 500 hectopascal map shows a stream of strong winds about 5 kilometers or 3 miles above the surface that circles the North Pole. This is the jet stream that has a strong influence on our surface weather. Let's focus on the two gold circles. At the surface, there is a weather system south of Greenland, indicated by the green swirl. This surface system appears below an abrupt change in wind speed at 500 hectopascal, where the pink stream abruptly turns green, and the winds have slowed down. We will explore these connections between the jet stream and surface weather later this semester. We have arrived at our last slide. In Unit 1, we have quickly surveyed the meteorology we will investigate in depth this semester. We have focused on the measurement of temperature, pressure, wind, and precipitation. In summary, we note the following 5 points. First, consistent, accurate, and continual observations are important to record and forecast the weather, make seasonal climate forecasts, and study climate change. Second, physical principles are used to determine the behavior of the atmosphere. These include conservation of energy, see box 1.1 in the textbook, conservation of mass, see box 1.3 in the textbook, and conservation of momentum, see box 1.6 in the textbook. Third, instruments are combined in weather stations that are increasingly automated, providing both measurements and interpretation of measurements in real time. Fourth, networks of observing stations are important in providing a complete view of the weather. And fifth, both surface measurements and measurements of vertical profiles from radiosondes are needed to understand and predict the weather. That concludes Unit 1. Next week, in Unit 2, we will continue our exploration by investigating ways in which we represent the weather. Thank you for your attention.